Okay. Whew. So yeah, we had the 2D genotype, which was a very direct, oh, you can't see, thank you. There, much better. We have the 2D genotype, which is the idea of represent this board. This one is an M, or 10 by 10, but this could work for any arbitrary n by n. Make like the matrix or a list of lists of size like n by n. And n of those cells will have a queen. Maybe it's like a binary encoding effectively where you've got like zeros, which represents no queen, and 1, which represents a queen. By the way, this is a valid solution. So with this genotype, we have almost 4.5 billion different possible configurations, which isn't that bad, really. But remember, we aren't really interested in smaller versions of these problems. We always like to geek out about arbitrarily large versions of these problems where n is a pretty big number. So as, like, what is 64? So what is 100 choose 10? Yeah. Right, so a 10 by 10, like this grows fast, times 10 to the 13. So that's a lot of possible configurations. But if it was unclear what I mean by if it was a 10 by 10 board, 10 times 10 is 100, and we choose 10, right? So that's a big number. So an alternative is, well, what if instead we have like instead of a 2D list, which is workable. I want to be clear, it is entirely workable. You could implement this and it'll work just fine. When I say work, I mean like it'll function. I don't mean it'll necessarily find good results very fast. For sufficiently small problems like 8 by 8, it'll probably actually do pretty fine. And so you can do it. You could implement it. There's nothing wrong with this implementation or this representation more specifically. But let's see if we can do better. Because remember, we're always talking about that gap. In that n by n configuration, in that like square, that list of lists, we know we obviously could encode every possible like valid configuration and every possible correct configuration. But we're going to include a lot of ones that we don't really want. Like, for example, like I could, in the configuration of n by n with 10 queens, that will include a configuration where this bottom row is all queens, which we know is obviously not correct. So is there a way we could eliminate those things from our representation somehow? Was that clear what I mean? Like, of every possible configuration of queens on the board in this 2D encoding, which is very direct, we will have one of the possible things that can be represented is an n by n board where the bottom row is all filled. There's also going to be one where the middle, like this row is all filled, and then this one, and this one, and this column, and this column, and this column, and that diagonal. Those will exist, which is fine, but we know that that's not a valid configuration, right? It's quite obviously not a valid, I mean, it's not a configuration that will hit the mark of they're not attacking each other, because they're all, that's the worst case scenario. They all can attack each other. So could we have a representation that eliminates that? Well, what about a 1D list of coordinates, right? It's still relatively direct. It's not as direct as like a 2D matrix, but a 1D list of coordinates is still relatively direct in the sense that like the translation from the encoding to the phenotype, it's natural. I mean, at least it's natural because we're used to coordinate systems, right? We've been doing it for like a decade of your life, right? So if we were to do this, we would have a list of length n, and each value in the list would be a queen's xy coordinate. Like I was saying, it's a little less direct, but it's still relatively direct. But we do need some translation mechanism to go from the coordinate system to what it means in the phenotype. It can also absolutely represent all possible configurations. Each queen, so yeah, for the size of the search space, there are n queens to be placed. Each queen has a xy coordinate, and there are n by n possible positions for the queen. Therefore, with this encoding, the search space has a size of n times n to the n. So in this particular one, for 8 queens, we actually have 64 to the power of 8, which is a lot worse, actually. So, okay, we actually took a step in the wrong direction. Can you think of why this encoding is worse? Like, what's the intuition as to why this encoding actually gives us more possible configurations? Take a moment, think about it. You can come up with the solution.
I would assume it could be that all queens are on the same square.
Exactly. This configuration allows for queens to be on the same square. Not even like a case where all of them are at location 0, 0, but where 2 of them are at location 0, 0, right? Like it's every possible overlap where they are literally on the same square. So that's actually why this one gets worse. So, all right, well, this 1D encoding is actually a little worse. To be clear, it can work. This encoding is functional. Not particularly good, but functional. If you implement it and you run it, you'll see the evolution happen. Yeah, it's worse since it's possible for queens to be placed in the same xy coordinate. So now how about this? Integer and permutation. Well, since the queens, at this point we need to be paying attention. Everything makes perfect sense, but if you're not really paying attention, you might get lost in the description. Since the queens are not to attack one another, they can't be in the same row or column. I mean, also, they can't be in the same diagonal, but let's focus on rows and columns. We don't want our queens to be in the same row and column. As soon as we had a configuration where at least two queens, were in the same row or column, we immediately know that it's wrong. At least it's not going to satisfy the constraint that none are attacking. You might remember I talked about a little while ago, we can reformulate this question as an optimization problem where you minimize the number of queens in conflict, but the ideal scenario is where 0 are in conflict. But anyways, is it clear what I mean? If they are in the same row or column, it's automatically there's at least a pair of queens attacking each other because they're in the same row and column, right? So since each column can only have, or can have only, what would be the better grammar here? Each column can only have one queen. Each column can have only one queen.
Both are equivalent. I'd say both.
You think they're fine?
Equivalent.
Flip a coin?
Yeah.
You think, what? Oh, interesting. Only have one queen. Interesting. We have, see, I'm more along the lines of but if there is a more correct way to do it, I mean, I should probably do it that way. All right, anyways, back to talking about this. Okay, so can only have one queen in it, an integer encoding could be used. All right, so have a list of size n. All right. The index in the list corresponds to the x coordinate. And the value in the index corresponds to the y coordinate. So let me draw what I mean. I'll do it in Paint because I know it doesn't really show up very well. So let me open up Paint. You're not allowed to make fun of me. So if I have a list, and let's say we have I do have like a bamboo board, but I'm not very good with it. 1, 2, 3, 4, 5, 6, 7, 8. Okay. In here will be a 4. Go with me, that's a 4. 2, oh, this is terrible. 2, 6. Okay, you know what? Oh my God. 2, 6, 1, 2, 5, 3, 0, whatever, right? What this would mean is, okay, imagine there's a board below here. I'm not going to try to draw it because I've decided paint is terrible. If I had a board here, it would mean in this column, there's a queen in like the 4th row. In this column, there's a queen in the 2nd row. And this would guarantee there's no 2 queens in the same column. It would be impossible because there's only one value in this column. And the value at index 0 is where this queen, like it's the x coordinate. You seem unconvinced.
No, I'm convinced it just kind of sounds like Sudoku a little bit.
It is just Sudoku.
Now,
At that point.
we could take this a step further because if we go back to 7, 3, 0, 1, nope, that's supposed to be a 1, 4, and 5, 0, 1, 2, 3, 4, 5, what do I have a repeat of? 4s. 6, there. If I make this a permutation, basically meaning I can only ever have one of each value here, I now also can ensure that no queen can be in the same row, right? So we guarantee that the x coordinate for each queen is unique because there's only one index 0 in this list, right? And the index is the x coordinate. And we also guarantee that the y coordinate is unique because this is a permutation of unique values. If there's a 4 here, I know no other queen can be in row 4 because there's no other 4 in this list. I know that because it's a permutation. Cool? So now we've got a very interesting, this is rather indirect. It's more indirect at least, sorry, it's less direct, let's say, than the other representations I'd say, because there's a little bit more like hoops to jump through to get from the encoding to the meaning, like the phenotype to the genotype. There's more hoops to jump through to do that translation. It's not too bad, but there's a little bit more to it. But now we have eliminated one. It's not possible for 2 queens to be on the same cell, which is, okay, good. We're back to where we started. But it's also not possible to have 2 queens in the same row or the same column. This doesn't mean they're not in the same diagonal, though. In fact, I know that these must be in the same diagonal because, okay, well, if they're right next to each other and one's 1 row lower, Any questions about this encoding? Now is the time to ask. If you haven't wrapped your head around it, please ask now. Okay. So, ensure you've got, okay, this would mean no 2 queens could be in the same row, and if you make it a permutation, they can't be in the same column. Perfect. So here we have 2, 5, 7, 0, 4, 6, 1, 3. 2, 5, 7, okay, 0, 1, 2, 3, 4, 5, 7, 0, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 1, 3. That would be like this encoding gets us, like this genotype gets us this phenotype. This phenotype would be encoded as this genotype. Pretty cool, right? Like this is clever. What I like about things like this, and I'm not just talking about like evolutionary computation, I'm talking about like really anything, right? Like it's not complicated. It's not immediately clear. It makes perfect sense, but if I told you, come up with a good encoding, you probably wouldn't come up with this right away. Maybe, but you probably wouldn't have come up with this right away. But you see it and you're like, oh yeah, it's clever. There's like a cleverness to it. It's nice. So what do we get out of this though? Like, what's the search space size? Well, it's a permutation. Here it's 8, right? So 8 factorial, well that's 40,000. That's way better than 40,320. That's way better than 4 billion. It's so much better, right? So this search space includes all possible configurations we care about, but it excludes a lot that we don't care about. But we still have that gap, right? We have that gap of, we're still including the diagonals. This encoding doesn't guarantee that we've excluded diagonals, right? And we know that if we could exclude diagonals, we'd be in better shape. But then again, if we had a way to guarantee that they weren't in the same row or column or diagonal, I mean, that would have solved the problem. So, yeah. There is a gap, okay. Okay, the above problems are common toy problems that are well understood under this. I've talked about this a lot, but I think it's important to emphasize. They're well understood and they're easy to reason about. That doesn't mean they're simple. They're simple to understand, but the problems themselves are very difficult. But to understand the problem, what it means, what a good solution is, all of that, we can kind of wrap our head around. And you ever notice, okay, let me go back here. Okay, so evolution, this is the real point I want to make, and then I'll come back to what I was about to say. These are toy problems. I'm not saying they're not interesting in and of themselves. I'm saying that they are commonly referred to as toy problems. That's all I mean. Because we can understand them, and they're a great, like, training ground. And when I say training ground, I don't mean like, oh, grab your Nerf guns and training wheels. No, I mean, like if I'm inventing a new modification to a genetic algorithm that I think is really good, I would use this problem to prove or to demonstrate to other researchers, like, look how good it is. Because it's like the common problem. TSP would be another example. So I don't mean, like, yeah, it's great to play around with and hack around with for learning purposes, but it's also a great place that, like, it's a good, like, benchmark. So, in practice, though, we've spent all of this time reasoning about these problems, finding that gap, and then making it smaller and smaller and smaller. But I don't want to give you a false sense of what you could do when working on an arbitrary problem. We use these algorithms on hard goddamn problems, all right, that are not well understood. That's the point. If there's a new novel problem that you come across and you want to use a genetic algorithm for example, and you're like, well, what's the gap? Look, if this is a hard problem and not well understood, chances are going from one encoding and reasoning about how small you can make it is not going to be that easy. It's not going to be obvious. It might not even be possible. It might require some weird mental gymnastics to get from one encoding to another, what a good genotype is, that you might not be able to come up with, not because you are deficient in ability, but because, like, no one else has, and if someone figured out a good encoding, they might get a PhD for it, type thing, right? Like, these are difficult things to do. So I'm showing you how good encodings can make a big difference. What I'm not showing you is, it's as simple as this to come up with good encodings. I want to be very clear about that. This is a very difficult thing to do. Is that clear? Cool. Now, what I was going to say a moment ago that was a little tangential to this, it's kind of funny. Like, a lot of these difficult problems, humans are kind of good at finding good solutions on their own, right? Like think of TSP, right? If I gave you a big TSP instance and you told a computer to run, it's going to use a lot of computational resources to find decent solutions. But as a human, you might look at an instance, you have it laid out in front of you, and you're like, you can kind of start connecting the dots and be like, that's probably pretty good, right? Same with like scheduling. Have you ever had to make a schedule for work or anything before? That's a hard goddamn problem. You give it to a computer, that's a hard goddamn problem. But a human, non-trivially, like it's difficult, but like we kind of have like this, we're kind of good at it, which is interesting, right? What I mean by that is I don't even really know. But that's where like the hope is, I think, when we're trying to reason about, like, for example, an encoding. Like what intuitions can we draw on? Like I'm thinking, okay, when I'm looking at a TSP instance, because I'm a human and I've been running around for 35 years and I look at an instance, I have a pretty decent understanding of like physical space. So I know if two dots are close together, I might want to connect them. If they're far apart, don't connect them. So there's like this okay, there's like that physicalness that I'm drawing, that my knowledge and experience with physical spaces I can pull on. That a computer is like, what the hell does it know, right? It can calculate a Euclidean distance, but what does that mean? So that's kind of the stuff we might want to think to. Is like, well, what's that intuition a human would have here that makes us kind of weirdly good at solving these problems, right? And because I now realize a lot of you haven't, like, raise your hand if you've taken theory of computing. Raise your hand if you've taken third-year algorithms. Okay, yeah, you probably haven't gone through a lot of this. Okay, most of you haven't. Okay, that's fine. With these difficult problems, I'm going to try to give like a quick little summary of one of the big ideas of those classes. Is there are some problems out there that we can like prove are like goddamn hard, like so hard, okay? And we have no good algorithms to solve these problems. They don't exist. We talked about this briefly at the beginning of the semester, right? We have an algorithm that might exist, but like, yeah, it's going to take longer than the universe has existed to even, touch the top of the iceberg. So, like TSP, we can make an arbitrarily large TSP instance, and then if I run, like, okay, I want to write an algorithm to solve it, it's going to take a long goddamn time. Or maybe I can write like an approximation algorithm that can come up with like good solutions. It's still going to take a while. It's going to take quite a while, right? As n approaches infinity, like these problems are getting harder and harder to solve, even with fast approximation algorithms. But a human can like look at that problem and do like what I just talked about. Like if it was laid out in front of me, I can just like start connecting the dots and probably come up with like a decent solution. That's what I mean there. Is like some of these problems that we know are really hard. For some weird reason, like our intuition can really help us a lot. I mean, jokes aside, like it's almost a joke though, because like, oh, we use AI to solve these problems. Well, our intuition is just based on heuristics that our brains have picked up and that we apply to everything anyways, which is just AI basically. Like that's what AI is, right? We try to come up with like heuristics to solve problems. Raise your hand if you've heard the word heuristic before. How many of you have you taken?
Explain to me what that word even is.
Okay.
I'm so confused.
So, okay, heuristic. If I say a word that you don't know, that's fine. I might need to rethink about the prerequisites for this course.
I'm sorry,
No, that's not. You don't need to know this in order to be successful in the course. It's just to get some of the bigger ideas. It might be worth. Yeah. Anyways, a heuristic. Okay. Raise your hand if you be honest. Raise your hand if you don't know what heuristic means, and it's entirely fine. Be honest. Really high. Was your hand up, or were you were thinking about it?
I'm just trying to remember.
Raise your hand if you've taken like an AI course though, and you don't know what heuristic means.
I'm taking 3 AI.
Yeah, okay, that's not your fault. That's somebody else's fault. Heuristic
I'm just bad at words, so I probably was told and then completely forgot the word.
could be with heuristic, and you'll hear the word heuristic in everyday life too, but a heuristic simply means like a rule of thumb that you kind of follow to solve a problem, right? That's basically what it means. Like, if it's dark out, it's probably nighttime. You don't know. Like if you were locked in a room forever and then finally someone opens the curtains and it's kind of dark out, you'd be like, oh, it's probably nighttime. That's like a heuristic, right? You don't really know, but yeah, chances are that's probably what it is. Why? Well, because you've seen this a lot, and that's just kind of a safe rule. For all you know, someone's out there with a black curtain outside the window and is like, haha, it's daytime. But you don't really know, but something you can draw on. A depth-first search, right? Who here took 162 with me, right? So if you did, or even if you took 162, you would have done the maze solver, right? A depth-first search is a heuristic, okay? It's a form of AI, it really is. But a depth-first search is a heuristic, where it's like, look, if you follow these rules, you will find a solution. It might not be the best solution, but you will find a solution. Happy, right? We use heuristics in our everyday life all the time. That's like how we navigate the world. It's almost like another level of abstraction. Is these like little rules we follow that might not be correct, but they get us around. And we're doing just fine. You've made it this far in life, you're probably pretty good at it, right? So that's what like a heuristic is. So AI is built on the same principles of where like necessary correctness isn't as important as like coming up with like a sufficient solution quickly. So like AI is like, it's heuristics, all right? So where was I going with this? Why were we talking, how did we go down this rabbit hole? Why did we start? Well, I just said the word heuristic. Whatever, we've got some built-in heuristics that help us like solve TSP. Sometimes it's really clear what it is, like TSP, well, we've got good spatial awareness, so, I can figure it out. But other problems, we might not even know why we're kind of good at it. We just kind of are. It's weird. So, anyways, point of this is identifying the gap is non-trivial. Finding a good representation is non-trivial. The only, like, you probably won't find one unless, I don't know, I don't want to give you the false sense of, follow these steps to find a good representation. No, it doesn't work like that. It doesn't. All right. Any questions about that little rant? We're good? All right. Common representation. So below is a collection of common representations. They can be whatever one needs it to be, like the 2D encoding above, that's entirely workable, but that's not like a run-of-the-mill common representation that you'd see. Some of these encodings fit well in a particular like form of evolutionary computation, like genetic programming uses trees, typically. It doesn't have to, but typically. Some of these encodings are effectively what define some other types of evolutionary computation. You could say the same thing about trees with genetic programming, but that's not necessarily true. But like evolutionary strategies as well, like the whole finite state machine encoding, yeah. All right, a binary representation. Well, this is just a list of zeros and ones. When I say list, I don't mean like a literal like list. It's just some linear collection of zeros and ones. It doesn't even need to be linear, really, like we talked about with the 2D encoding of the queens, but a binary representation. It's common for like a binary decision problem. Can be used to represent really anything though, right? Anything that you can represent on your computer, technically you could represent with some binary encoding with the sufficient encoder and decoder. Whenever you're using this representation though, it's often very indirect, okay? Like if you think of like the picture that like this, all this information on the screen is a 0 and a 1, or really a low voltage and a high voltage inside your computer. So that's clearly a rather indirect representation. It's almost like it's harder to get even like more indirect. Then we have integer representations. This would be a collection of integers. And we talked about some of these examples, like, well, we could use TSP, except We did end up with a permutation representation. But with TSP, yeah, we used the permutation representation, but we could have used an integer representation. We could have used an integer representation for the n queens, but in the end we decided on a permutation. What else we got? Ordering, allow all integers represented in Python. Okay, yeah. So the integers, like, well, what are they encoding? Well, I mean anything, right? Like with TSP, I was like, well, take a city, assign it a number. Boom, done, there. We got an integer. But maybe the integers really do mean like a number. Like that it's got like an intrinsically direct encoding because it's talking about a number. Or maybe, I don't know, we might have a very small set of integers we allow, like 0, 1, 2, 3, which mean like north, south, east, west. Like, what if it's like a string that's like the direction for a robot to move? Okay, 0, 0, 0, move north, move south, right? Like, whatever. The ordering of the integer values may or may not matter. For example, in that one there, 0, 1, 2, 3 being north, south, east, west, entirely arbitrary. The fact that 0 comes before 1 doesn't, like, we know with integers are ordinal, which is just a fancy way to say there's an order. What comes after 0? Does 7 come before or after 44? Before, right? There's an order to these things, right? Does green come before red? I mean, maybe, I don't know. Like, that's kind of a weird question. You might say, like, well, if you order them based on, like, wavelength, fine, but you just defined an ordering. The ordering doesn't exist. Like, integers in and of themselves have an intrinsic ordering to them. They are ordered. If I ask you what comes first, my shoe or my hat? Well, what's the ordering, right? There's no ordering. There's no, like, obvious ordering. So, like, what comes first, north or south? I mean, north? We don't know. It's arbitrary. So, although integers have an intrinsic ordering, we have to be careful. This is a very common problem that computer scientists have, by the way. Not just in this particular example, but literally anything, especially when you start using integers to represent things. Like if you start doing, like imagine, like some of our like AI machine learning algorithms that are very mathematical and they work with numbers. The fact, like if it's doing like regression analysis, yeah, this is going to be hard to explain because a lot of you don't have experience with this yet. I'm trying to think of a good example that makes sense. Like if I'm trying to draw a line, here. This won't be the best example, but I think it'll do the trick. If I've got these data points, I'm going to just represent them as lines. The length of the line, this is terrible. It's not working. My trackpad is like, well, that still won't really work because half the problem is like callousy fingers and as trackpad that's like trying not to be too sensitive. Yeah, you can't see those. Maybe I can make it bigger. I'll try one last thing. No, brush. No. 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 No, thank you.
I mean, it'll work.
Thank you, but no, thank you.
It'll work.
Imagine I had a plot of like cardinal direction, like northeast, southwest, and temperatures. All right? Why? I don't care what it's representing. It's just that's like, why do I have those two values? I don't know. Why do I have pairs of information? I don't know. And I've decided to say, okay, 0 is north, 1 is south, East is 2, and 3 is west. Okay? So I take each point. I'm going to have to draw this with a marker. Hopefully for you over there, you can see it. You're probably more likely to see it if I draw over here. Can you see that decently well? Right? So I've got like 0, 1, 2, 3, and I've got like temperature over here. Right? And I'm saying, okay, data point number 1. Oh, it's north 40 degrees. All right. And I just start, the next one is, okay, 0, 1, 2, and that was east. East, 20 degrees. East, 25 degrees. South, 4 degrees. South, 30 degrees. West, 50 degrees, right? Like I'm going to start getting all these points. Right? Cool? You get this idea, right? But the problem is, we need to accept that the fact that this is 0, and this is the fact that north came before south was arbitrary. There's no reason for it to come before south. I just said 0 north, 1 south, no east, south, whatever. I can't remember the numbers even. It was entirely arbitrary. Now, a lot of these machine learning algorithms will try to draw a line. And let's say it's trying to classify temperatures. I don't know. And it's trying to go, it'll go like that, right? But like it's trying to draw a line based on the math, like based on the numbers, right? And the fact that numbers have orderness is important for this type of math, this type of machine learning to work. But the fact this was 0 and this was 1 had nothing to do with the data. We actually introduced an orderedness that doesn't exist, that the machine learning was trying to exploit. Because that's how the machine learning was like working, these forms of machine learning. So computer scientists often make this mistake where they start accidentally, let's use integers. You've now introduced an ordering that a lot of algorithms will try to take advantage of that doesn't exist. So your algorithm is trying to learn something from the data that was never there to begin with. Huge problem. So be aware of that. Was any questions about what I just said? This problem comes up in a lot of forms of AI, machine learning, and there's a lot of strategies we have to fix it. And by the way, there are like, this is an aside, but it's important to know if you take any other machine learning algorithm or you are just a computer scientist in general. I'll finish this point and then I'll come back to what I was just about to say. So yeah, 0, 1, 2, and 3 mean north, east, south, west, but we got to be careful. North is not less than south. So the order of the elements of the collection may or may not matter. Sometimes we're using integers and the order matters. Sometimes we are using integers to just represent something where order doesn't matter at all. And sometimes we're using integers to represent something where order does matter. We just have to be very aware of what we are doing here. So, and here's the thing, right? Some people will even like make a distinction where like, okay, yes, this is like using 0, 1, 2, 3 to represent north, east, south, west is an integer encoding. But some people are very careful to be like, it is, but it isn't. Because it's a subset. Where like, yes, they're integers, but like, this could have been NESW. Like they didn't have to be integers, right? So like whenever you have like a finite set of available values, sometimes people like to differentiate there. Clear? Unclear? So they're integers, but they don't need to necessarily mean anything related to integers. Now what I was going to say, going back to this idea, where like order may or may not matter, and sometimes order is complicated. Right? Take the days of the week, for example. And let's say, for the sake of our discussion right now, let's say Monday is the first day of the week. I know you could be like, it's Sunday. I don't care. It doesn't matter for right now. Okay? So like Monday is the first day of the week. So does Tuesday come after Monday? Yeah, that's reasonable. Does Wednesday come after Monday? Yeah. Thursday? Yeah. Friday? Saturday? Sunday? It does, but it also like comes before Monday, right? This is like a circle, right? So you can be like, it comes before and after, where like now we have an orderedness, but the orderedness is also related to like a distance, where they can get further away, but also then back closer to each other, like a circle, right? Right? Yeah, cool. We're used to this in our everyday lives. We use clocks. So we understand this idea, but sometimes we, forget it. So sometimes the integers have no meaning for ordering. Sometimes they absolutely do, and sometimes it's complicated. You just have to be very careful. I'm just trying to impress upon you, it's not as simple as like, let's use an integer encoding. Next. No, it's let's use an integer encoding. What are the implications? Is this a good idea? We just have to think of these things. All right. Yeah, okay. Consider the problem of programming a robot to traverse a maze. The set of possible integers could be 0, 1, 2, 3, meaning north, south, east, and west. The robot needs to take 10 steps. There. That's an encoding. There's an integer encoding. The order of these numbers don't matter. The fact that 0, 1, and 2 comes after 0 and after 1, but 0 comes before 1, that doesn't really matter. But it still will work for our purposes. A permutation representation, well, an order value in a set, multi-set, basically it's an arrangement of values in some sequence. It could be the case like TSP. Now remember with TSP, the fact that the things that we had a permutation of were integers was arbitrary. I could have used letters. I could have had a permutation of anything. I just used an integer to represent, okay, that's city 0, city 1, city 2. I could have literally called it like Halifax, Antigonish, Toronto. I just needed a permutation of these cities. The fact that I labeled them with integers was entirely meaningless. It didn't have any value. It was just an easy thing to do. And there are some like engineering reasons why it's handy inside your computer, because you just take the city number and that's the index to calculate the distance. It's the whole thing. Anyways. And another thing too is all you really need to have a permutation is not a permutation of numbers. You need a permutation of things. And the values that you have a permutation of things are, depending on how you think of them, don't even need to be unique. It's just, if I have 3 red widgets and 7 green widgets, I just need shufflings of those things. They don't even need to be unique amongst themselves. They just need to be a shuffling of those things. We can start splitting hairs to be like, well, you just take each green widget and assign it some integer 0, 1, 2, 3, and then that's still the same thing where they are unique. Fine. They aren't really the same thing if we think of them this way. Yeah, I get it. But the point is, they don't need to be a set where each value is in fact unique. They just need to be, we have some defined set number of things that we want to have permutations of. Very important. Consider the problem of finding English words from a given multi-set of letters. There. A, E, G, M, N, T. Right? All right, find permutations that spell, there. Here's a list of possible chromosomes, right? So the point is, they're not unique, and that's fine. I just need to shuffle these things. Cool? Cool. Yeah. And then real number problems. These problems are hard. And something like a GA, by the way, which you've been doing, raise your hand if you haven't started assignment 1 yet, by the way. It's fine if you haven't. I'm just curious if anyone hasn't. It's probably a good thing. GAs, typically you don't really, you absolutely can use a genetic algorithm. there are a lot of like tricks to make it work, but typically you don't want to use GAs for real, like floating point number stuff. They tend to work better in more discrete spaces. There are other forms of evolutionary computation that are specifically designed for real number problems. But a real number problem is like, okay, a collection of real, and by the way, I'm always like, I'm going to try to do my best to say real number, floating point number. But I think we all know at this stage that when I say real numbers in the computer, we all know I really mean floating point numbers. There's like a limitation there, right? So if not, well, you can't represent real numbers in a computer. Tough. Anyone know why you can't? There's too many of them. That's basically it. You just can't. Right? Right? Remember that whole thing, what comes after 1? Yeah, 1.0001? No. You missed a lot of numbers. 1.000001. 1.0000. I still have a finite number of bits. I can't possibly represent all possible real numbers. So we use our hack of floating point numbers to just make it work. I know I might feel like I'm being overly pedantic, but it's important to make sure we are remembering this thing. All right, so this is called the Ackley function. A lot of times with real number, you know what, we'll pick up here on, this is worth talking about. We'll pick up here on yeah, whenever. Anyone have any fun plans this weekend?